Hello, my name is Yuri, and I'm a graduate student in statistics at the University of Wisconsin, Madison. In this video, I'm going to present our work, a variational approximation for analyzing the dynamics of panel data. I hope you enjoy it. This work is motivated by the need for analyzing panel data. Let us see what that means. In this type of data, we look at one subject and acquire longitudinal measurements, and we do this for many different subjects. Notice that neither the spacing across the subjects may not be the same, and nor the number of measurements. Plus, the starting time point of records is not assumed to be aligned. In this case, our overall goal is to characterize the dynamic of the panel data. Now, if we fit a global model to these measurements, say via a regression model, we get what is traditionally called the fixed effect model. However, if we are interested in the specific participant's prognosis, we must introduce an offset to adjust the global model to the specific participant's measurements. This is often known as a random effect. When we account for both fixed and random effects, in the statistics that is usually called the mixed effect model. What we really want to do is to model these data in a generative fashion. Doing so will offer the number of benefits. First, we can consider our data to be a continuous function of time. However, we may only be given a part of the trajectory of the measurement, which we call observed, while the remaining part of the trajectory is unobserved. Of course, in real-life application, we are not given the continuous measurements, rather some discretizations of the observed and unobserved parts of trajectories. Then, our high-level goal is to find an efficient generative model to interpolate and predict future data. In fact, our goal is to understand the dynamics of this trajectory. It is very natural to think of generative models for these trajectories as differential equations. It turned out that introducing stochasticity into these differential equations allows us nicely handle random effectrons that we previously discussed. Let's see how we do this. Assume that we can take an observed trajectory and map it using an encoder to a latent probability distribution, which we assume to be normally distributed with parameters mu and sigma. We can use it to sample the initial value of the SDE trajectory. Given the initial value of the trajectory, in the combination with an SDE solver, it is possible to train a decoder to generate the observed data to arbitrary accuracy. Given the nature of differential equations, we are able to generate prediction at any continuous time points for both interpolation and extrapolation. We have made a design choice to use differential equations as a generative model for trajectories. The following question is whether we should choose an ODE or SDE route. SDE does offer a mechanism to easily incorporate our mixed effectron. Let us see what else are distinct pros and cons of these approaches. For example, ODE is fast and offers a large number of libraries, while SDE also has a good software support. It is believed to be slower than ODE, but it directly offers uncertainty incorporation in the model. Let's start with an SDE solution to this problem. This equation describes the changes in the latent variable z over time t, given a drift f and a noise sensitivity function L. Our interest is particularly lies in the last term, which turns out to be convenient to incorporate mixed effect term in the model. Instead of a direct application of SDE, we decided to consider the smooth approximation of it. First, we apply Won and Zakai theorem, which states that the solution of SDE can be approximated asymptotically by the solution of the following equation, where phi is a suitable set of basis function. Then, under some assumption on a basis function phi, random samples b, and the noise sensitivity function L, we arrive into the next equation. Last, assuming form of a drift f and the resultant function g, we get our mixed effect ODE as a smooth approximation of SDE. Notice that gamma can be a neural network, which makes our derivation a mixed effect neural ODE. Let's see what are the benefits of smooth approximation. First, it models uncertainty similar to SDE. And secondly, it is important to notice that now, for a fixed W, we can directly apply an ODE solver. Okay, let's look at what our construction looks like. First, we use observed data to encode the initial value of ODE in latent space. Then, given distribution of mixed effects and using ODE solvers, we generate a distribution of trajectories in latent space corresponding to the observed time steps. Finally, resulted trajectories are passed through decoder to generate output in a data space. Now, let's take a look at our loss function. Given variational autoencoder nature of our model and that randomness is coming from Z and W, Our loss is based on the typical elbow loss. However, how should we define the approximate posterior distribution QZW? We apply a standard practice to parameterize joint distribution. Now, to define our distribution, we need to define three other terms. While QW and QZ0 are simple, what is Q of all Z except Z0, given Z0 and W? Given the nature of constructed trajectories, mixed effect neural ODE results in a special parameterization of approximate posterior QZW. You can see that given Z0 and fixed W, we can completely define Z at any time step using ODE, which means that ZT is not a random anymore, but a degenerate distribution, which leads to the following form of joint distribution of Z and W. This special parameterization of approximate posterior QZW leads to the new elbow-based loss. The feature of the proposed loss is that we are required to use samples of Z0 and W, which reconstruct observed steps exactly. However, this is not efficient. How can we improve the situation? Here, we can use the ABC method. It suggests to approximate the indicator function with a more relaxed version based on epsilon neighborhood of y and some distance d. In other words, the indicator function gets a value 1 if z is in the epsilon neighborhood of y. You can see that introducing mixed effect to model trajectories allows generating personalized prediction. After learning the model and training data, we are able to generate the distribution of trajectories corresponding to the mixed effect. At test time, we'll make use of the observed temporal data for a previously unseen test subject X. Given the learned distribution of mixed effect W, we want to find a sample which minimizes error with respect to observed data. This selection provides the most appropriate mixed effect corresponding to the testing data X. We call this process calibration. This selected mixed effect allows us to create a personalized prediction and use it for extrapolation, which is different from taking the average. Let's take a look at some of our experiments, which are based on temporal datasets with different correlation structures to represent mixed effects. Considering rotation MNIST, we'll look at how the number of samples used to select mixed effect during calibration affect the extrapolation power of our model. As expected, decreasing the number of steps for calibration yields a smaller number of steps where the extrapolation is meaningful. We perform experiments on two different types of brain imaging data, which contains information about two groups of patients, normal and abnormal. Results suggest viability of mixed effect neural ODE for modeling longitudinal 3D imaging data. For other experiments, please refer to our paper. That's it. Thanks for your attention. Our code is available in the GitHub link below, and feel free to contact me over email.